So in this case, we are going to consider our revision, which is from the question paper that was written in April 2024 for these exams. We want to consider and see how we're supposed to attempt these typical questions. Take note, you're given the drawing instruments and non-programmable calculators may be used, and the question paper consists of 6 pages and a formula sheet of 6 pages. This is what we had. And if we go through our instructions, guys, as usual, make sure that you read your instructions. That is the most important. Definitely have to answer all questions. Number the answers according to the numbering system used in this question paper, and according to the degree of accuracy, how to round off your answers. You're not given, so you can use the 2 decimal place. You can use the 3 decimal place. It's up to you. It's up to you. But you have to indicate that. So that is the condition of our questions. We were not given that instruction about rounding off your answers, so you can even use the 3 decimal places. So we're not going to waste much time. Let us quickly rush through our questions. Number 1, this is what we are given. And if we are to consider this part, we can see that we are working with the alternating current theory. So they're saying on the first part on number 1.1, with the aid of a neat labeled RC integrator diagram, indicate this type of passive filter. Indicate this type of passive filter also. Indicate this with aid of a diagram. You have to indicate this. Remember, from your RC integrator diagram, we are going to have our resistor. Okay, then it's going to be connected to the capacitor this way. So there's actually nothing there that you need to consider that much. And also take note of your voltages at the output and at the input. So this is actually the part of your input. So you're going to have your input, and this side, you'll be having your output. So considering the part of the capacitor, we are going to have the voltage drop that is across the capacitor, across the resistor. You must also indicate the voltage drop that is going to be across the resistor. So that is the condition of our question that we were given in this case. So this is what you just need, just a second diagram. So in explanation of this and further explanation, I just need you to see according to this part, we have got our RC integrator circuit. This circuit is shown in figure 1.34, which is this part. So you can actually have it this way with the CR differentiator, the output. So they're now talking about the description there, but in actual sense of the diagram, you can have it this manner. So I do not know, because it depends actually maybe with the textbook that you are using at the end. So I'm not going to talk about much there. All right, so let's consider another part and see of our question, which is a continuation. They are saying choose on 1.2 the correct word or words or from those given in brackets, right? Only word or words next to the question number 1.21 to 1.22 in the question. So here they are saying in an RC integrated circuit, the mark period of the applied square wave is greater or smaller than the RC time constant. What is the relationship when you are to consider this? What is the relationship? All right. So the time constant is much larger than, okay, let's go back to that again and see here, because if you check your answers with the memo there, you might not understand what I'm going to explain here. So for us to understand this, let's go back. This is the one that we're talking about here, our RC integrator. And let's check here. They are saying the time, as we have to consider it, we have given the explanation, RC is and integrator is only approximate unless the output voltage is relatively small compared with input. Or this is the explanation that they're trying to say. That is, the time constant of the RC circuit is much larger than the period of what? Of the input. signal. The time constant, as we are talking about the time constant, which is your tau. Remember, your time constant is tau of an RC circuit, which is the product of resistance and what? Capacitance. They're saying is much larger, meaning to say it is greater than the what? The time period is greater than the time period, which is the period of the input signal. It is greater than. The time constant is supposed to be greater than. All right. Now let's go back to our answers and see how we're given it there. Because we are saying the time constant, tau, is supposed to be greater than the period, which is at the other input. Now here they gave us this statement in a vice versa. The marked period of the applied square, which is at the input, is great, which is this one. Is it greater or not? It is not, guys. This one is smaller because the time constant is the one that is greater. So this one is smaller than is compared. This one is supposed to be a smaller than. Okay. So be careful on that one because there you're given is greater, no, because it's supposed to be time constant greater than that one. Then on 1.22, the square waves or the sine waves indicate the presence as well as the type of error during the testing of electronic circuits. Which one between the square wave and the sine wave? So that one is for a square wave. The square waves are the ones that indicate the presence as well as the type of error during the testing of electronic circuits. So that was the part of your theory there. So guys, I do not know, pending with your textbooks, also understand how they try to explain that. Then on 1.3, we are given the voltage phasor diagram of series RLC TechNote. It's a series RLC circuit that you are given there. Yes, the following. So remember, if it is a series RLC circuit, we've got a resistor, an inductor, and also a capacitor. So they gave us the voltages which are to be taken across each. That is across each, in this case, the voltage across the inductor, the voltage across the capacitor, the voltage across the resistor. We're given as the voltages in this case. So these are the phasors that we're given. Then the question was on 1.31 to draw the phasor diagram out of this information. Remember, this is our series RLC circuit. As we had this in our N4, we are going to consider. All right, so here I'm just going to try have a sketch of how it was supposed to just look like. So remember, we're just going to have our vertical. All right, this is too much, guys. I just need something less, or let me just have something that is a little bit smaller. All right, so we're just going to have our vertical and also the horizontal. So this part, I'm just going to use a broken line since we do not know exactly where that is going to be. So as we know, our angles going in the anti-clockwise direction, they are taken as positive. As we go in the clockwise direction, the angles are taken as negative, starting from the reference point, which is along what? X-axis. So this one, I'm going to represent this one with a continuous line. All right, because this one we do understand where it is, because that is our reference point, which is at what? At 0 degrees. So we're simply going to take our angles from the 0 degrees. The first one is VL, and also understanding the relationship between VL and VC. What is the relationship? This VL and VC are in a straight line as we consider a series RLC circuit. They are in a straight line. They form a straight line, meaning to say, if we are to add the angle for VC, which is 38,32, and add to this angle of 141.68, ignoring this negative, you add these angles, you're supposed to obtain 180 degrees. This is to show you that they are on a straight line. They are on a straight line. So the moment you indicate one angle, it's either you're going to work with VC or you work with what? With VL. VL is 38.32, meaning to say you're going in the positive, but just below 90 degrees. This is 90. So if we indicate a straight line like this, guys, the straight line that we are indicating here is the one that is affecting the two. So the moment you indicate to say this is the angle for VL, at the same time, you're indicating the angle for VC. So I'm just going to indicate it this way. Let's say approximately this is where we have our angle of what? Of 30, 38.32. Let's say this is our angle of 38.32 degrees. So it means our VL, which is positive, is the one that you're indicating here. So that's our VL 242.5. And the angle there was 38.32 degrees. All right. So the one that is now left out from the same horizontal axis as our reference axis, but going this side, as I said, negative angles will be on this other side. The angle that is left out there is the minus 141.68, which is in a straight line with the VL, but this is our VC. So that's our VC there with a negative. That's 164 with a negative 141.68 degrees. So you can just write, since VL is greater than VC, you can just write VL minus VC. Let's move on to another one. We've got VR in that case at an angle of minus 51.68. As we can see, it is exactly in phase with IT because they're at a certain, at the same angle there. Same phase. There's at the one angle, minus 50, minus 51.68, minus 51, negative angles. We are going in the clockwise direction. So this will be 0, this will be minus 90 degrees. So minus 51 is in between these two, between 0 and what? Minus 90. That is where we are going to have our angle in between. Just indicate any angle that you can just have there in between there. So you can just have your line this way from the origin like this. All right, let's just approximate. This is where we can have our angle at. Okay, let's just have an approximation there. So meaning to say this is going to be here. That is the angle taken from the reference, which is at 0 there, going this direction of clockwise because we are considering a negative angle. So this is the direction. That's negative 51.68 degrees. So the angle is affecting the two things, VR and IT. They're in phase. So you can indicate your VR in that case. That's 61.8, and also the angle that is presented there, which is negative 51.68 volts. And also, as we saw, they are in phase with what? IT. So we're also indicating IT at the same time there. That is 5.15, and the angle being the same, negative 51.68. So that is in amperes current. So that's your total current. If you move on to VT, it's what? At 0 degrees, same as resistance. So meaning to say VT, our total voltage is at 0 degrees. So that's our VT, which is in phase with what? Resistance. So that is 100 at an angle of 0 degrees. Remember, this is how you're going to have these indicated on your face. So they can even give you this. I told you guys how to analyze to back to the diagram, from this back to the diagram. So make sure that you go through the introductions that I referred about this. So that was just a direct question, guys, 3 marks. So in your illustration, just be fast enough, guys. There's nothing that is much complicated there. And notice the angles and also the relationship of these two in a straight line. Okay, in a straight line, that is these two in what? In phase. Is the same angle in phase. So that is the condition. So on that question, on 3.2, that is now 1.32. Calculate A, the reactance of the coil. The reactance of the coil, as we can consider that we have got what? VL in that case. So we can consider the reactance of the coil. So how can we have the reactance? We have got VL, we have got the current, VT. So let's consider, because this is a series combination that we do understand that in a series, the current is the same. The total current is the same. So how did you obtain the voltages? It was current times the, here a resistance, current times the reactance, current times the reactance. From the total current that you had, the product of that current and resistance, that's the voltage across the resistor. Current to the reactance of the inductor, which is our coil, it gives us VL. So meaning to say from there, we can calculate this reactance because we can see that, all right? So that's 1.32. So the part of A, from the total voltage, I mean from the voltage that is across the inductor, because we're talking about what? The coil inductor. We do understand that is the total current times what? Times XL. So what is that you need? That is XL, the reactance. So you're simply going to divide by what? The total current, because you are given this. So divide by the total current. That was going to give us the value of XL. Just like that. So we have this. What is our total voltage? I mean, the voltage across the inductor. Our VL, as we are given from this part, that is 245 at an angle of what? 242.5 at an angle of 38.32. So you're going to substitute the part of VL, that is we are given 242.5 and also the angle, which is 38.32, divided to what? The total current as it is given. Remember your total current, it was 5.15 at an angle of minus 51.68. So you're going to substitute that. That was 5.15 at an angle of minus 51.68 degrees. So that's it. You're going to have the reactance there of the coil of the inductor. Back to your complex numbers. Remember, in polar form, you're going to divide. The angles you're going to subtract. So as follows, you're going to have R1 over R2. Remember the angles, theta 1 minus theta 2 is supposed to subtract. So meaning to say, if these two, you're going to divide. So what we're going to obtain, you're going to have 47.087. And the angles you subtract. Remember this, theta 1 minus theta 2. So it was going to be 38.32 minus this. So it's going to be minus 51.68. So that will be a plus there. So that is going to give you 90 degrees. Remember also that you're dealing with the part where you're dealing with the inductor. So you are saying this is purely inductive at that moment. You're dealing with the inductor only. So it must be at positive what? 90 degrees. If you're calculating XC, if it was XC, you're supposed to get an angle of what? Negative 90 degrees. If you do not get that, it means all your calculations there are actually wrong. All right, so let's consider the B part because we also have the reactance of the capacitor there. So as we had the first one, going to have also for the capacitor. So what is going to be our reactance for the capacitor? From the manipulation that we made, it simply means the reactance of the capacitor will be from the voltage of the capacitor over the total current, because we saw that the total current in a series combination is the same. So that was going to give us the value of XC with our VC. If you have to consider our VC, that was 164 at minus 141.68. So we have the voltage there. Okay, take note here, we've got our voltage. So we're going to substitute that. That's 164 at an angle of minus 141.68 and divided to the total current. That's the one that we used on this part. So already the total current is there, 5.15 at an angle of what? Minus 51.68. So that was going to give us the value of XC, just like the previous case, dividing your R1 and R2, meaning to say in this case, you're going to divide these two. That means you're going to have the value of XC, which is 31.845. And for the angles, you subtract, just like what we had. So this angle is going to give us an angle of minus 90 degrees. That is, you're just considering this angle, then we subtract. So it's going to be minus this. So definitely that was going to give us a negative 90 degrees. So the first part, you calculated your reactance. So that's our reactance in ohms. And also here, we have got our reactance. So that was it. And considering the resistance on C of the series resistor, meaning to say this time we are supposed to use the voltage across the resistor, our VR. All right, and we have our VR in this case. Remember, this is our VR and our IT is also given. So we're going to divide those two. All right, so that's the C part. We need the resistance this time. So that is going to be simply the voltage across the resistor over the total current. Remember, in series, current there is going to be the same. So taking our VR, remember, our voltage across the resistor was 61,8 at an angle of negative 51.68. And considering our total current, this is our current as we had before, 5,15 at an angle of minus 51.68. So this is it, guys. Divide your numbers here. You're going to obtain 12. And the angles, if you subtract, that was going to give you a 0 degrees. So that is to show us that truly this resistance, because you say this resistance and the total voltage are supposed to be what? Are supposed to be in phase. As we can see that the total voltage was at an angle of 0 degrees. That is the same condition of our resistance at 0 degrees. And that is the one that we have here on our phasor diagram. You can see that the resistance and the total voltage are in phase. They are at 0 degrees. So that was it on our first question. As you can consider your AC theory, questions can be like that, where you need also to relate with the theory sometimes, and also the diagrams where they are needed. So you need to consider another question, which is from our continuation, and see how it was given on question number 3. On question number 2, sorry, which is the part of our power supplies. So you were given in this case that is the power supply of a Samsung TV. It uses a pi type filter. So remember, if you're dealing with a pi filter, it can be LC pi, it can be RC pi. So according to our question in this case, we are given that with an input DC of 18 volts. So this is our input across the first capacitor. As we consider a pi filter, remember, you're going to have capacitor 1. So it depends, is it an RC or is it an LC? So here we are given that it has an inductor, meaning to say we are considering an LC, meaning to say there are 2 capacitors there, capacitor 1 and also capacitor 2. Remember, guys, from your introduction. So we're not going to waste much time there. So they said on this part, this is across the first capacitor. So meaning to say the voltage across the first capacitor that they are referring to is our VDC. So we are given VDC of 18 volts. Then the inductor is an inductance. Also, you're given the inductance value, which is 5 henries, and a wire of what? 20 ohms, which is the resistance. So you can call this the series resistor, or you can just refer to is R1, which is 20 ohms. Calculate the output DC voltage. That is the one that is across C2. So remember, we've got a VDC, but this one is the output. At the output across C2, remember, this is referred as what? VDC bar, like that. At a load current of. So given a load current, that is our IDC that you're given at that moment, which is what? 50 milliamps. So how can we calculate this? Okay, I talked about this, guys, from our introduction. So I need also us to go through our formula sheet so that we do understand some of these formulas just as a recap of what we had before. So if you're to consider your formula sheet, in that case, if you're to consider your formula sheet, remember, I talked referred about this formula that is also can be used, which refers to the VDC at the output from the VDC that we had at the input minus IDC RC. So this can be used in simplification. We can have this. So using this formula, guys, because you can see we've got everything that we need on this formula. So simply, what were you going to do? It was simply to substitute our values that we are given. So I need us to take this formula and substitute our values. As we can see that VDC there at the output can be calculated. That was our VDC minus IDC around 1. So with this, we're going to substitute our values that is at the output to determine the VDC at output. We're going to substitute 18 minus everything is there, guys. As you can see, our IDC is also there, which is 50 milliamps times 10 to the exponent of -3 times our R1, which is same as our RS, and that is a 20. So that was going to give us our VDC, the one that we need, and that was going to give us 17 volts. All right, so let's consider another part. As you can see, this one was direct question on 2.2. Explain the reason why the capacitors in the filter circuit of a power supply are connected in parallel and not in series with the load. Why are they in parallel? So this is just a condition where we need to block the AC signal. So the major part here is that it blocks AC signals and passes. So in this case, it's going to pass the DC and passes DC signals. That is the major purpose of us having the filter circuit of a power supply being connected in parallel, not in series. Then considering on 2.3, you're given to calculate the voltage. That is the drop in the output voltage, the drop that happened in the output. If a power supply of 25 volts at no load voltage has a voltage regulation of what? 8% and is connected to the load. So the output, meaning to say you're talking about what? At full load. That is 2.3. Let's just take our information that we are given there. So we are given the voltage, to calculate the voltage at full load actually, given the voltage at no load, which is supposed to be 25 volts. And also we are given the voltage regulation as a percentage. So that is our percentage voltage regulation is given to be 8% according to our information. So the question is, how are you going to obtain the voltage that is at full load? Remember from our formula that the percentage voltage regulation is given from what? Voltage at no load minus the voltage at full load. Everything divided to the voltage that we must have at full load. So if you have forgotten this, according to your formula sheet, guys, you've got these formulas also presented. So if you check here, from our formula sheet, we have got the percentage voltage regulation, which can be given. That is the condition that we have there. So meaning to say we just need to substitute our values there and have it. So this is times 100% to have it as a percentage. But as you consider this decimal part, for you to just remove that, the moment you remove this percentage, this one, the moment you just remove this percentage, just write it as a decimal. All right. So in this case, guys, I'm not going to indicate this. I'm going to remove this, just divide here by 100, which is going to give us 0.08. So you can just substitute this. So that's 0.08. So it's a decimal that you are using there. You have already divided that. So the voltage that we have at no load, we are given, that is 25. And what about the voltage at full load? We do not have. So this is the one that we are supposed to calculate, remember. It is the same also voltage here that we have the voltage at full load. So as we can see, we can have this as an equation. For us to solve, that's an equation. So let's cross multiply so that we can solve for VL. That's times 0.08 times the voltage at full load. 1 is going to multiply this side. So it's going to be 25 minus the voltage at full load. So considering that we need VL, let us just collect our terms where the VL is the voltage at full load, guys. That is going to be a plus. So that's simply 0.08 plus 1, which will be 1.08 V full load, which is going to be 25. So let's find this voltage, guys. As you can see here, just simply going to divide by 1.08, 1.08 both sides. So this is going to give us the voltage that we need at full load. So from these calculations, we were going to obtain 23.148 volts as the voltage that is at full load. So this one, it was just a matter of use of the formula. We have the percentage voltage regulation from where? It was taken from where? That is the question. It was taken from where? Then on this other part, they are saying we are supposed to draw a neat labeled circuit diagram of a shunt voltage regulator. So you're considering a shunt voltage regulator and briefly describe its operation. They are saying you are supposed to draw that. So a shunt voltage regulator can actually be given in this manner. So according to what we have in this case, we can have this as our shunt voltage regulator, which we're going to have our Zener diode resistor connected to the transistor. Then we've got our voltage division that is happening to the V out. So this is VBE, like the voltages that we have across the transistor. So this is simply representing our VBE, and this is VZ for the what? For the voltage that is across the Zener diode. I also talked about this in another class. So guys, we're just going to refer also to the notes that can actually help. So in this case, how the supply power is regulated, because you need to regulate the power. The value of the Zener diode, which is DZ, is selected in such a way that the bias VBE of the transistor T1 is low enough to keep the transistor in an unsaturated condition. So that is what you need to consider. And on the second part, you're given that if the supply voltage increases, the Zener diode, which is the Zener voltage of the that you have, which is our VZ, will remain constant, but the base bias VBE will increase. So as we consider VZ, it is going to remain constant. At that moment, VBE will increase. This causes the transistor to be driven to greater saturation in order to let the collector voltage drop. And the last part is that this fall compensate for the increase in supply voltage. And in this way, the output voltage is stabilized. So as you have to consider your circuit diagram and your explanation, this will be enough for you to have this. So it was just a 7 mark. The 14 mark there is just like the total of the whole question, considering from where we started. So that was for 7 marks, guys, to have your diagram. And I think this is direct and straightforward. You just need also to revise your diagrams. It's not about calculations, guys. As you can see here, it was actually like half in terms of calculations, in terms of diagrams. The first part, it was actually 2 marks. This is 3 marks where we need calculations. The rest is the diagrams and explanation, 9 marks that we have here for explanations. It's just 5 marks for calculations. I'm not saying it's like this always. It can be like that. So this is simply to tell you that also revise your diagrams and your theory, because in another exam, it can be more of the theory than what you expect in terms of the diagrams. All right, on 3.1, we were given briefly describe the functions of the following components of in a common emitter amplifier used on a communication system. On 3.11, the voltage divider, RB1 and RB, these are voltage dividers. So these ones, they supply voltage to the junction. All right, so these ones supplies voltage to the junction. That is the condition of our voltage dividers, these voltage dividers. Then the input capacitor CB at the base, which is the base capacitor, it blocks the DC signals, whereas A signals are passed. So this is the purpose there. It's gonna blocks DC signals. So this one blocks DC signals, whereas AC signals, are passed. So that is what you need to also consider in your revisions as part of your theory there. I'm not going to talk much. Let's consider the part of our calculation on 3.2, where we are given the following values of a fixed bias voltage amplifier without thermal components. So we do not have those RE, RB components. As you can see on our presentation, we do not have those resistors like RE, the CE that we used to have, even the voltage dividers in this case, they are not even given. We are just referring, guys, here, according to this, this is just a simple fixed bias common emitter that we are to refer. Just a simple one. So on that information that you are given, we need to consider our, just gonna show you one or two from our introduction. Remember, I actually referred to this before we talk of the equivalent circuit. I want you to just see the circuit diagram because I talked about these guys so that we do not waste much of the time. If you consider this is our part of our common fixed bias common emitter. All right, no, do not consider like to say when you're representing the equivalent, don't include this, just the basic one. We do not have those the part of the collector, the part of the emitter, there we're gonna have the resistor, capacitor, what. The voltage division, it will be just basic that you're given. Basic. We do not have like RB1 because on the other one, we're gonna have RB1 and RB2 where we talk of what the voltage division, the one that we talked about there. This is just a basic one. A basic one. So on that basic, we are given the information, the VCC, and all this other information. And they are saying, calculate 3.21, the collector emitter voltage. Collector emitter voltage. All right. If you consider your formulas on a basic, remember from your RC, because we are given RC there, I also want you to go through your formula sheet so that you understand me, guys. Let's go through our formula sheet and have a basic review here. All right, remember when we talked about this RC, this is just a basic. So we're not here to these ones, we are here. These basic ones, guys. Here, remember RC there and RB. So between these two, we can see that RC, where VCC is, also VCE is the IC. So we can take this formula, guys, and utilize this. We can take this formula. Okay. Sorry for that. Let's hope it's not going to affect us here. You can take this formula and utilize, because what we need there is the VCE. All right. Let's go back to our calculations there. But I talked about this on an introduction. So guys, just go through those introductions because of time, guys, we might not finish. If you want to discuss where it was taken from, this and that, there will be a lot of things to consider. So I'm just going to indicate as what we have there. So our RC we saw from our formula sheet that is just taken from VCC minus VCE over what? Over IC. And what is it that you need there is the VCE, and everything is there. VCC is there. RC we have, IC we have, so everything is there. We just need to make this the subject of the formula. So how can we make the subject? Just cross multiply these two. They do multiply. So it is going to be the product of RC and IC. So we're going to have IC, RC is equal to, one is going to multiply this whole part. So that part is going to remain as VCC minus VCE. What is it that you want to make the subject is as the VCE, and it is carrying a negative. So take it there so that it becomes a positive on the other side of your equation. So that's VCE is going to be equal to what? We are having VCC already on the right-hand side. So we take IC, RC to the other side so that it becomes a negative there. So it will be IC, RC, not a positive, no, but a negative. So you're going to have your VCE, which is equal to VCC. What is our VCC according to this? A plus 20. So you're going to substitute, that's 20 minus IC. You've got your IC there, which is 14 times 10 to the exponent of minus a milliamp. That's minus 3 times RC, which is 1 kilo ohm. That's 1 times 10 to the exponent of 3, a kilo ohm. So that was going to give us the collector emitter voltage, guys, which is our VCE. And that was going to give us 6 volts according to our calculation from what we have there. It was going to be 6 volts. That's our VCE. So also, if you consider your memo, it was actually a mistake, an error there to obtain this. They used a plus there, and they obtained VCE, it was gonna, if you use a plus, it will end up as something like 34 volts. This cannot happen that VCE is greater than VCC. No. Remember this, we're talking about what? A fixed bias where we have got 1 as the supply. And what is the supply? It's VCC. VCC is the supply of this. So VCC cannot be less than this. But VCC, because it is our supply, is supposed to be greater than, bigger than VCE. This one is supposed to be bigger. This is our supply. We cannot have the supply less than the voltage. That is what it is distributing inside there. No. So in actual sense, VCE is less than VCC. Okay, this one is less, but VCC is bigger, greater than that one. So let's just correct also. They just made a wrong manipulate, like just manipulating the issue of the signs. I don't know how do they get a positive. Just a mistake, guys. If you take this side, it becomes a positive. If you take this other side, it becomes a negative, not a positive there. So let's just correct. They do happen, these errors. Do not panic, guys. Do not panic. They do happen. They do happen in your question papers. A lot of them, they do happen. The best current, IB in that case, we need the best current. If we were given IC and the gain, we're going to use that, but we do not look. They want you to calculate the beta gain later on. So to have IB, there's no way. Let's find a formula. Let's find a formula that is capable to determine this. IB. Remember from RB here, from this one, we can use it because we have RB, VCC, VBE is given, and what we need is IB. So we can take that formula, substitute our values, and determine the value of IB in that case. All right, so we saw that. I'm just going to write it here, guys, because of issue of space and time also, 3.22. So we saw that from RB, we can calculate IB from RB, because RB is equal to VCC minus VBE over what? Over RB. Sorry, guys, over IB there. Okay, so let's see what we can do. We can make this the subject. So also be good with change of subject. You see, if you are not good with change of subject, even if an error happens, you do not notice that. So just use as it is. Be good with your change of subject. So just going to cross multiply. Remember, we need to make IB the subject. So let's cross multiply. This will be IB, RB like this is equal to 1 times this other side. So 1 is going to multiply the whole of this part. So it's going to be VCC minus VBE like this. What is that you need? You need to calculate the value of IB, this one. This is IB. So what is needed? That you need to remove this. You need to remove that RB. So just divide by what? By RB both sides. Divide by RB both sides like this. So you're going to have the value of IB. So just like that. So IB is equal to this. The whole of this part that you're seeing, that's VCC that you are given there. Remember, your VCC is given 20 volts minus VBE, we are given that's 0.7 over RB, which is 800 kilo ohm. 800 times 10 to the exponent of 3. So that was going to give us the value of IB, which is the base current. That's going to be 0, that's a lot of zeros there. 4. 1, 2, 3, 4. That's going to be 24125 amps. But as we do understand that base current best to be expressed in microamperes, it is best that you write your IB in microamperes. So how do you convert to microamperes? You use the opposite, multiply by 10 to the exponent of 6. Whatever that you're going to get there, if you multiply by 10 to the exponent of 6, which is 24,125, that answer will be automatically in microamperes. Remember your conversions, guys. I've been talking about these conversions. You want to convert to micro, so you multiply by the opposite, the inverse of that. Remember, micro is times 10 to the exponent of -6. You use a +6 in order for you to convert it to that. To convert it to, you use the one opposite. Just remove the negative. There's a positive, remove a positive to convert to that. Just Opposite of what you want to convert to, guys. Beta gain. Remember your beta gain because we have IB there, so we can calculate our beta gain, which is the ratio between the collector current and the base current. This one, guys, we have, these were also given from our formula sheet. So IC, we're just going to take our IC. Remember our IC, it was 14 milliamps. So we're going to substitute 14 milliamps, 14 times 10 to the exponent of minus 3 over IB, which is 24.125 times 10 to the exponent of negative 6. So that was going to give us the value of our beta gain. That was going to give us 580,311, something like that. So this is what you're going to obtain as your beta gain. So that was it, guys, on question 3.2, considering your 3.2 to the end. So with this, we're going to consider the other part, which is 3.3. Let's see what we are given. Let's see, on 3.3, we are given on this part, that is a supersonic radio. It has a fixed bias. So take note, it has a fixed bias with an input impedance of. So take note when you are given with this, where you are dealing with the part of your H parameters, once you talk of the equivalent values, this and that, H parameters, where you are given, in this case, calculate the values of the collector. They need you to calculate the value of the collector resistance and the base resistance, which is very rare for you to be asked this type of a question. But in this case, it was like that. And they are saying, with the precise method, if the following information of the transistor is known. So from the E that we are just saying, as we can see, there is the letter E there, the letter E, this letter E. It is telling us something. What are we dealing with? We are dealing with a common emitter. So this is from a common emitter. We are dealing with a common emitter in that case. We can see from that information, which is a fixed bias voltage. So what about the input impedance? They were given the input impedance. Remember, when you're dealing with these guys, I talked about this on our introductions, that there are impedances that you talk about, which is of the entire stage. And there is the input impedance of the transistor only. So if you are given like this, these are of the entire stage. So they are giving us ZI of the entire stage, which is 1,169 kilo ohms. And the output impedance, that's our Z out, again, of the entire stage, which is 1.96 kilo ohms. So these ones represents the entire stage. Okay? Because we're going to need, there's Z1, there's Z2, which is for the transistor only. So they are saying from these ones and from this information that we have so far, we are supposed to determine these values, RC and RB. All right. So I want you to just take a closer look, just a recap of what we had, because I talked about this, like I said, on our introductions, guys. If you consider this part, I referred, this is the common, the fixed bias common emitter amplifier that we're talking about, where we do not have the emitter resistor. It's just a basic one. And from the equivalent circuit, I described this. If you still remember, I talked about this circuit that you're going to have on the equivalent circuit, Z1, which is now considered, which is the Z-in, which is considered there. We can see that there is RB that you're going to have. At the output, the Z-out, what is affecting there? The Z-out, we are affected with what? The RC and the Z2. So here we'll be having, let's have this one as this, okay? There is something that I just need to add. There you're going to consider to say, you'll be having your Z2, your Z1, yes, just like Z1. And this will be your ZI. So it's affected by RB and Z1 of the transistor. The ZO, which is the output, there is affected by what? RC and Z2 of the transistor. We do not have anything special because there we do not have like any other resistor that has been added at the output, we do not have anything that is there. So in that case, you have to consider that, like I talked about this, guys, if you still remember, just a recap. In that case, you have to consider that your ZL will be taken as your RC. Remembering these now by precise method as they stated there. So you're going to talk about this part, guys, all this. So which part was going to help us? If you take a closer look here, because you're talking about finding of RC and RB from those input and output. But as we can see that in our calculations, as we have to consider the first part, you need to calculate RB. You have to calculate RB there. But from there, you must have Z1. And Z1 is have to be considered from ZL. Remember, ZL represents what? ZC. Let's go back here. Let's go back here. Let's go back here. ZL is supposed to be equal to RC. So it was not going to be easier for you to work with input first. It was going to be easier if work from what? From the output. Because from the output, you do not have any relationship of RB considered to RC. From the input here, we see that this part here, this part of our this here, where we talk about the ZL, it depends. Whatever that you're going to need there, it depends on RC because RC is equal to ZL. So it was best for you to start with what? With the Z out. Okay, so I'm going to analyze from there. Z out is representing the entire stage, as I explained. This one is for the entire stage. Okay, let's get rid of this. We need this part on. So the entire stage, this one. But as it is of the entire stage, it is in parallel. We talk of Z2 parallel to RC at the output. At the output. So you're going to notice that RC is the one that you need to calculate. What about Z2? Because Z2 is also an output impedance, but of what? This is of the transistor only, which is the one where we need our H parameters now. So as you can see, these are the stages that we're going to take. So meaning to say us now, we have to do the opposite now. Instead of us, right, we're going to start with where the Z2 of the transistor only. We bring it back to the formula here so that we can find our RC. That was how they wanted you to answer this one. It was going to be a lot if you try to figure it out from the first stage, but you have to take it from that last stage. All right, so that's it, guys. Sometimes exams can be like that. So this is 3.3. All right, so that's 3.3. So they're just going to consider one or two things. All right. So we saw that it would be easier for us to start calculating RC. So we're going to focus on calculating or determining RC. And we saw that RC is in the formulas which are taken from the output impedance of the entire stage, where the output impedance of the entire stage at the output, we are going to have the two impedances in parallel, Z2 parallel to what? To RC, which simply means you're simply talking about Z out equal to Z2 times RC over the sum of Z2 plus RC. We can see that we do not have Z2, which is of the transistor only. This is of the transistor only. This one. So the transistor only. This is of the entire stage. Entire stage. So we need to calculate Z2, which is of the transistor only. From where? That is where we have to use our H parameters now. That's why we have to use H parameters. So this part, if you have forgotten, guys, those formulas that I was showing you from the notes there, they're there from your formula sheet. So you have to present also from your formula sheet. All right, let's go back to our formula sheet. Remember this, you are given this. All right, we have to consider the H here. If you consider this part, Z1, Z2, we have this. Okay, so we are considering the Z2 here. This is of the transistor only. Then we talk of the Z out of the entire stage. They gave you also that. This one, Z out of the entire stage. So on a condition that we are considering RC and Z2 only, we're going to take this formula that Z out is parallel to, L parallel to Z2, where ZL is our ZC. All right. This is the explanation. Maybe in a better explanation, they indicated this here. Better way. RC parallel to what? To Z2. So we need R2. We need RC. But we have to find what? Z2 first of the transistor only, from here. Transistor only there. All right. So guys, you just, it's not that much. It's not that much. I just want you to understand that this one is not that much. Just know your formulas, guys. So it was going to be 1 over, let's substitute this H or minus, that is considering our output conductance there. Then we're going to consider our forward transfer ratio, multiplied to the reverse, everything over, that was HIE, which is for the input impedance plus RS, the series resistor, where we are given that RS is 0 there. So just substitute, guys. So that's Z2. Remember Z2 for what? Transistor only. So this will be 1 over, let's substitute, guys, our values as they are. So the part of HO is given 20 micro there. So that is 20 times 10 to the exponent of -6 minus HF. Your HF, that is 60. So you're going to have 60 times your HR there, which is 2 times 10 to the exponent of -4. 2 times 10 to the exponent of -4, everything over our HI, which is 1,2 kilo ohm. So that's 1,2 kilo ohm. 1,2 times 10 to the exponent of 3 plus our RS, where RS is taken to be what? Is taken to be a 0. So they had to force you to calculate this Z2 of the transistor only, which was going to give you 100,000 ohms, which is actually the same as 100 kilo ohms. If you want to write this way, you can write it as 100 kilo ohms. So we have the part that is affecting the transistor only. From that part of the transistor only, let's try to figure out how can we obtain our RC, because these two, they are now the Z out of the entire stage and the Z2 of the transistor, they are there. So what we need is to find RC. So let us play with our mathematical skills here. Find or determine RC. Make RC the subject. So let's cross multiply here. So Z out is going to multiply these two. So it means Z out is going to multiply Z2. The same Z out is going to multiply RC. So it multiplies everything. So take note that it multiplies everything. So it's Z out times this. It also multiplies this, because there are two terms there. Is equal to 1 multiplies this part of Z2 RC. So what we need is to find RC, and there are two of them, one on the left and the other one on the right. So just make sure you collect the terms that consist of RC. So that's Z2 RC minus Z out RC, like this, where RC is the one that we need and is common. We can factor that out. That was going to remain with what? Z2 minus Z out, which is equal to Z out Z2. What is it that we need? We need to find RC. So simply divide by the bracket. Remember your N4, guys, mathematics calculation that you had manipulation, even from your N3. Mathematics, you used to work with change of subject, this and that. Yes, let's get rid of that and try to recall all those. So that is it. So we're just going to substitute there. We have our Z out of the entire stage. Remember, our Z out there is what? Z out, that is 1,96 kilo ohm, which is same as if multiplied by 1,000, it's going to be 1960 ohms, 1,960. So you can substitute your values there. That's determining now the value of RC from what you are given. The values are there. The values are already there. So what is that we are given? Remember your Z out, we say this is 1,96 times 10 to the exponent of 3, or you can just write it as 1,960 multiplying what? Z2 of the what? Of the transistor only here, which was given as 100,000 or 100 times 10 to the exponent of 3 over what? That's Z2 minus Z out. Z2 of the transistor only, 100 times 10 to the exponent of 3 is supposed to subtract that of the entire stage, the one that we had, the 1,96 times 10 to the exponent of 3, just like that. So this was going to give us the collector resistance. And that was going to give us 1,999,184,007, this and that, ohms, which we can also write as kilo ohms. You can even just raise these decimals, guys, to 3 decimal places like that. You can even write this in kilo ohms if you want, or just leave it like that. That's your RC, which we are saying is same as writing a ZL from our equivalent circuit. So that was our condition there. So if we check now, we need RB. So let's think of determining RB. Okay, so there we worked with RC, and we have to figure it out from the Z out of the entire stage. What about RB? Where are we having our RB? From the Z in of the entire stage. We do understand that this is a comparison, that is the relationship that is happening between Z1 and RB, parallel to. Okay, I showed you guys at the input. What is it that you have for the equivalent circuit of a common emitter amplifier? You're going to be having Z1. There'll be Z1 here and RB, so they'll be parallel. Just like here we have RC and Z2. So here must have Z1, and the part of our Z in, that will be the parallel combination of those. It's only that here, guys, I did left out the like Z1, and this is our ZI. So these two in parallel, your RB and Z1 in what? In parallel. The product over some, but not forgetting that from our precise method now, this is how you're going to have what? Your Z1. So all this you have to calculate. Your Z1 is going to be there. Where ZL is equal to what? Where our ZL is equivalent to what? To RC. That will be the condition. If we are given any other, like we are given RL anyway, then we're going to consider this. But here we are taking ZL equal to RC direct, because we do not have that part of RL, any other resistor given. There's nothing there. Nothing. So we are going to take our ZL as our R, as our RC. That is the part now where I was saying we are limited, because you need the RC that you just calculated now for you to work the part of the transistor only. All right, no problem, guys. Let's consider our question. So from this, we are going to also have our Z1. Remember, this is entire stage. This is the transistor. This is the transistor only. That's T only, transistor only. So meaning to say, working with the Z1 of the transistor only from our H parameters, we saw that this is given from HI minus, we are going to have this as HF, that's HF times HR times ZL, where our ZL in this case, because we do not have any RL there, so ZL is going to be equal to RC. So we're going to use RC there in place of what? In place of ZL, over 1 plus HO RC again, which is our ZL. So everything is there. We calculated this right now. So meaning to say we're going to have Z1 of the transistor only. Just substitute H parameters, guys. Your HI is given, common emitter there, 1.2 times 10 to the exponent of 3 minus your HF. Your HF is given, that is 60. The reverse, that is also given, 2 times 10 to the exponent of minus 4 Your RC is the one that you calculated. That is the one that you're referring as your ZL. All right, all right, all right. Let's just see here, guys, so that we do not have a lot of things to consider there. Remember, when you calculated here, you're calculating RC 1119,184. So that is the value that we need here, 199,184. So this is divided to 1 plus HO, which we have it here, our HO, remember, that was 20 micro. So you're just going to substitute there. 20 times 10 to the exponent of negative 6 times RC. It's a repetition, the same RC that you had, the same RC that you had as it is. So it was going to give us Z1 of the transistor only. And that was going to be 1,176.932 ohms. The transistor only has been calculated here. But we are saying, what is of the entire stage, of the entire stage? How are you supposed to use this now on the entire stage, to have the entire stage? Because Z1 of the transistor only is also playing a role on this entire stage. That's we're going to take our formula for the entire stage, where RB is the one that we need to calculate here. So it follows that from Zi, which is the input, we are going to have Z1 times RB in parallel over the sum. So we need to make RB the subject. So cross multiply, Zi is going to multiply this. It also multiplies this. So there are two things to be affected there. So that's Zi times Z1. Okay, plus the Zi is going to multiply RB there. So that's Zi times RB equal to 1 is going to multiply this other part, which is Z1 RB. You need to find RB. RB is RB here. So let's make it the subject. So it's going to be Zi. Z1 is equal to Z1 RB. You take this to the other side, it becomes a negative there. So it's going to be Zi RB. Okay, so you need to make RB the subject. So just factor it out because it's common here. So that's our RB is going to be into Z1 minus Zi like this. And this is Zi, Z1. So divide by the bracket because you need RB, Z1, Zi. Just divide here also by Z1, Zi. So this will cancel. So therefore, we're going to have our RB calculated from this formula, Zi times Z1 over what? All right, there's a subtraction. We divided by the bracket. There's a bracket. It's minus. There's a minus here. Minus here. There's a minus there. So that's Z1 minus Zi. Okay, just hope you also figured out as you're making the subject to say, how is that possible? There's a bracket divided by the bracket. So that's a minus there. So the Zi, remember, this is for our entire stage. That's your entire stage. And this is for the transistor only. So we have it, guys. Everything is there. What is our Zi from the information that we calculated? I mean, that we're given before. The Zi is the one that you're given here in 1,169 kilo ohms. So you have this. So you're going to substitute that Zi that we are given, which is 1,169 times 10 to the exponent of 3 times Z1, the one that we just calculated of the transistor only here. 1,176.932 over what? Z1, this one, the Z1, this one, as it is, minus Zi. So you're going to have 1,176.932 minus Zi, the one that we had of the entire stage. Remember that part. That's 1,169 times 10 to the exponent of 3. So with this, you're going to have the resistance that is across our base, which is the base resistance. And that was going to be 173,453,5 436 ohms, something like that, which you can just try to have it to kilo ohms. If you divide by 1,000, you're going to have 173.45. This was going to change into a 4. Okay, that's in kilo ohms. So that's the value of our RB there. So questions can be like that, where you need the manipulations to manipulate this change of subject. There is a lot that you need to consider there. It's not that much. You just need to know your formulas. As long the formula, you know it, okay, this is going to be my formula, then it's not going to be that much. You can even subject direct on the formula as long you understand the formula to be used there and how to use the formula as you are given the information. So it depends how the values that you are given, what are they representing? Substitution into the formulas, manipulation of change of subject, everything has to be considered in your calculations. You have to consider everything, guys. So if we consider question number 4, you are going to be having our operational amplifiers there, and 4.1 we're given to briefly explain the following terms with the reference to operational amplifiers, and the 4.11 was the input offset voltage. So remember, that's the necessary difference between the bias voltages at the input to obtain a zero output voltages. So that is our part of input offset. The necessary, that is, you're going to consider this as the necessary difference. The necessary difference between bias. So you're going to have the bias voltages, at the input to obtain. So this is given to obtain a zero output. That's a zero output voltages. So with this, you're going to obtain 2 marks for that. Then on 4.12, the inverting input, as we consider that is the terminal which we connect at the negative that has got an antiphase. So that is simply the input terminal as we consider an op amp. That is the input terminal of a differential amplifier, which produces an antiphase. So in that case, it produces an antiphase, which produces an antiphase output. So that is what we have to consider when a signal is what is applied. When a signal is applied. So that is the major part that you will need for 2 marks. Just 2 marks, guys. All right. 4.22, it was to draw the circuit diagram of an inverting operational amplifier. That's 4.21. We need for an inverting amplifier. So remember, this is from your N4, guys. You had your input resistor. This is connected to the negative. So the inverting, remember, it will be connected to the negative. So that's negative, positive to our feedback. So this is now going to the feedback. And from there, we have to relate to the what? To the output. So that is the condition which is important in our presentation. That's the input voltage and also having our output voltage and considering our feedback resistor and at the input, which is, we can call this R1. So that was our diagram. And from there, they gave us 4.22, which is a continuation from the same because the input signal of an operational amplifier in the inverting mode, in the what? Inverting, which is the one that you just drew there, the inverting amplifier. They gave us the input, that is our V1, or you can just write as VI, in that case is -2 volts. The input resistance, as we saw from our diagram, there is R1 there, which is given 15 kilo ohms. If the output voltage is 20 volts, you're also given the output, which is 20 volts. Calculate the feedback resistor, which is RF. So how do you obtain this from your inverting op amp, the one that we are having here? How can we obtain the value of the feedback resistor? So remember, from our output, we can have this as we had from our N4. Say the output is equal to minus RF over Rin, which is our R1. You can just have Rin or just write as R1 times the times the input, which sometimes they're also given. If they divide this by Vin, they will give you this as Vin over V out over Vin. You divide, like divided by Vin. They can divide this. So it will be V out over this Vin, which is equal to the minus affect this. So it will be minus RF over R1, which is our Rin. They can give you this from your voltage gain. Remember your voltage gain formula. So what is it that you need is to calculate RF. So you're simply going to make this the subject, multiply this side by R1. We use also the negative there. So meaning to say our RF was going to be, if you multiply this side, it was going to be V out over V in times R1. But also with the negative. So you're going to divide by that negative this side. So it will be a negative like that. So that is our RF as the change of subject. So that's minus our V out, just have to substitute our values. The output is 20 over the input, which is minus 2. So definitely the negative and negative was going to cancel there. All right, times Rin, which is at the input, we are given 15 kilo ohms times 10 to the exponent of 3. So that was going to give us RF. As we can see already, this part here represents a kilo. So just multiply this part. 10 from 20 over 2 times 15, which is 150. So it was simply going to give us 150 kilo already, the 1,000. Or if you can just use the 1,000 as it is, guys, but just know that the 1,000 there simply means a kilo. So that is 150 kilo ohms. So that is the value of RF that you were asked to determine from the presentation that we already given this. So it was just a matter of what? Substitution. All right, let's consider another part of our question, which was on question 5, integrated circuits. Our integrated circuits, as we are given, what should be done to the unused inputs of a CMOS integrated circuit when it is connected to a circuit? The CMOS, we are talking of the complementary metal oxide semiconductor. That is the complementary metal oxide. So this is the metal oxide semiconductor. That is what they're trying to talk about there. So what is it that is needed? What should be done? So remember, on your precautions, one of the precautions that we have is that all unused, which is the unutilized inputs, must be connected to VDD or VSS. All unused, all of this part, all unused, which is the unutilized, can have that way, unutilized inputs. You talk of the inputs there. All these unutilized or unused inputs must be connected to the voltages, to the VD, the terminals must be connected to VDD, or it can be connected to VSS. That is the major part of your CMOS. So just make sure that you go through this in your revisions, your theory. 4.2, you're given, indicate whether the following statements are true or false, writing only true or false. The first part is given that the CMOS integrated circuits have lower noise immunity. All right, this is actually false, because as we do understand, guys, remember, two important characteristics of the CMOS is that they are characterized by high noise immunity. High noise immunity. And also they are characterized by low static power consumption. Static power consumption. These are the major characteristics that we high noise. By there, they're saying low, lower. No. So this is false. All right. So then on 5.22, then they're saying these CMOS integrated circuits are susceptible to static charges. Like, okay, this is susceptible to static charge. Why are they considered like that? Now they are saying because that is the reason of their output, low reactive input. Is it because of that? No, that's because of as a result of leakage current. This is as a result of what? Leakage current. So this is actually false. It is as a result of what? The leakage current. 4.23, as soon as one works with the circuits of the CMOS integrated circuits, the power supply to the circuit must be switched on. That is false. As we are to consider the CMOS, this, remember on your safety precautions, major important part is you're supposed to double check the test equipment set up for the proper polarity that is given on our VDD and our VSS. You must check for that. Do not just switch on. This is the major part. Remember this one, guys. You're supposed to be very, very careful also as you are to consider your simplifications. On question number 6, we need to consider as a continuation there and see how these questions also can be given. All right, so on this part of our question, in this case, let us consider our question 6 and see how the question was given. They are saying, in that case, all right, sorry for that. We need this part here. That is, you are being asked to draw a neatly labeled block diagram of a general closed loop system and briefly describe how the load condition is kept constant. How do you keep the load condition constant? All right, so in this case, I'm just gonna show you according to your diagrams how they need you to have this so that as you are to revise, you know also what you are required to answer your question as. So this is what we have as our electronic phase control, considering a closed system. They've got the reference input, comparator to the RC trigger circuit, which is to the load, and we're going to have the transducer. So on this part, they are saying the comparator compares the feedback signal from the load. That is the major part now that you need there. The comparator compares the feedback signal from the load with the reference signal. As soon as the load diverts, an error signal appears on the output of the comparator. So that's where we have our comparator for comparison there, which is used by the control circuit in order to bring the load condition back to normal. As we are given on our question that how are we going to keep the load condition constant? That is the condition where the comparator has to play a role. Comparator has to play a role in that case. On question number 7, test equipment with aid of a neat labeled block diagram. Again, we need a block diagram. Draw an instrument that displays the frequency of a periodic electrical signal, that displays the frequency of a periodic electrical signal. So remember, when you are dealing with the Schmitt trigger circuit, I'm just going to also show you this so that you can have our understanding, where we have got our V1 connected, that's to the Schmitt trigger, and to the counter, the time-based generator, and to the display. So that is what you just needed there. Just go through your notes, guys. Okay, your diagrams and explanations, they need also to be done. So that's the idea there of your Schmitt trigger circuit, which is the one that we are going to use as the part of our frequency display of the periodic electrical signal that you're given. Then on question number 8, which is part of our oscillators, we are given 8.1. If the total inductance of a Hartley, take note we are given that's a Hartley tuned, which means you're talking about what? A Hartley oscillator. They gave us there. Remember your formulas also if you're considering your oscillators. All right, I think I have this so that at least it can help us to understand what we have. But also, guys, go through your notes and presentations. It can actually help a lot. So this is our Hartley oscillator, as we gonna have our circuit diagram. All right, so that is what you're gonna have on your presentation, where the Hartley oscillator consists of an RC coupled amplifier using an NPN transistor common emitter configuration. R1 and R2 are the resistors that form a voltage divider biased to the transistor. So you have got all the explanations that you will need in your Hartley oscillator circuit. All right. So here I'm not going to talk about the explanation, even the diagram. I just wanted you to have your recap of what you're talking about. But the major part that we need are on the calculations that happen in this part, which is the oscillating frequency, and also the total inductance is given by. So remember these guys, because on your formula sheet, you are given these formulas. All right. Let's go back to our formula sheet. All right. So I'm just gonna have our formula sheet again so that we consider also the formulas, these formulas as we are given. All right. Remember from here, that is what you have to consider when dealing with a Hartley oscillator. So also with the advantage of your formula sheet, remember your formulas, guys. Remember your formulas. All right, so this is it, guys. I just wanted you to see like which part exactly are we talking about, so that if we have the formulas, we just, okay, understand. So they are saying there on our Hartley oscillator, they gave us that the total inductance is 10 millihenries. So that is our LT, right? So 8.1, you're given the total inductance, 10 millihenries. And the oscillating frequency, we are given your oscillating frequency, which is 300 kilohertz. This is what we have. What is the value of the capacitor in the tuned circuit? As we saw from the tuned circuit, the capacitor that is there is what? Is our C1. So we need to calculate the value of C1. From this information that we have, we can simply work with our oscillating frequency. Remember, our oscillating, just like the normal frequency. Remember how you calculate your resonant frequency. Your resonant frequency is equal to what? 1 over 2 pi, the square root of LC. But there we consider the total, and this is the capacitor value C1. From your, the same way that you calculate your resonant frequency, but you need to calculate the value of C1. So you can even make it the subject. You can make this the subject. So let's cross multiply. It's going to be 2 pi f. This is over 1. So it's going to be 2 pi f or this one multiplies here the square root of LT C1, which is equal to 1. Remember, I want to make C1 the subject. So you can even divide by this 2 pi f or this one as it is this one. All right, so let's just divide by this. That's 2 pi f or divide also this size 2 pi f or like this. As we can see, the C1 is there, but is under the square root. How do you get rid of the square root? Just square both sides. So you're going to square this. That is removing the square root. So you remain with LT C1, which is equal to 1 raised to the power of 2. That's 1. 2 raised to the power of 2. That's F4. Pi to the power of 2. That's pi squared. F to the power of 2. That's F4 squared. Everything is raised to the power of 2. And from there, we can calculate or determine our capacitance value by dividing by LT. So to divide by LT, if already there's a fraction here, you simply divide it here. That will be your LT, so that this can cancel. So that's your C1, guys, which is equal to this. So we took off the capacitance value, 1 over what? 4 pi squared. So you have to substitute everything there. So you're going to have pi squared, the frequency, which is our oscillating frequency, that is 300 times 10 to the exponent of 3 squared times our LT. the total inductance that we are given, which was 10 times 10 to the exponent of -3. So it's going to depend with the values, because there we do understand that capacitance, it's best for us to write this capacitance in microfarad, this and that. But there it will be best for you to see the values that you are obtaining on your calculator before you talk of the conversion to say, am I going to convert to the microfarad or to the picofarad? Remember, you have to multiply by the opposite of the conversion that you're going to make. So in this case, it was going to be 1 over, on our calculator, that 1 over, that will be pi squared times, open bracket, that's 300 times 10 to the exponent of 3. All right, so if you close this bracket, raised to the exponent of 2, then we're going to multiply to 10 times 10 to the exponent of -3. So this is what you're going to have. As you can see from the answer, they were getting 2,8, whatever that you have there, times 10 to the exponent of 11 from what we are seeing there. Value that raised to the exponent of 11, something like 2,8, whatever that you have there, times 10 to the exponent of -11. You're talking of capacitance. Which value will be best to use on a condition like this when you have got -11? We can target the picofarad. Remember, the picofarad simply means times 10 to the exponent of -12. That's picofarad times 10 to the exponent, these two. That is the same. So how do you convert to this picofarad, this one? How do you convert? Because we want to we use the opposite, like I said, in whatever conversion. If you want to convert to picofarad, multiply by the opposite. This is your picofarad, this one. Just remove this negative here. Your answer will be converted to picofarad. So if on this answer that I'm having, this 2,8, whatever that I'm having there, if I multiply this answer, guys, this one that we are seeing here, by 10 to the exponent of the opposite, you just put a positive there. It was a negative. Now you use a positive 12. The moment you do this, your answer will be automatically in what? In picofarad. So this is the conversion that you can have. So on your calculator, this is what I'm trying to say. This was our calculator here. On our calculator, as it is, just multiply this by 10 to the exponent of what? Of 12, like this. The answer that you are getting, 28, this, you can even fix this to 3 decimal places if you want. 28,145. This answer that we are getting, it is automatically in the picofarad by multiplying by the opposite of what we had. So meaning to say we're going to have 28,145, which is what? Picofarad. Automatically we have converted to the picofarad. So that is the idea there that you need. If you're working with conversions, just understand what does it mean, this? It's a minus, so the opposite of it. If it was microfarad, micro is to the exponent of -6. So how do I convert to this? I multiply by the opposite, 10 to the exponent of 6, with a positive. The moment I do that, my answer will be in the microfarad. There we saw that the picofarad was going to be easier to work with than to work with the microfarad, because the microfarad there we are talking of -6, from -12, guys, to -6 by just mere looking. That was going to be a lot. So considering the other part of our question, which is question 8.2, you are now given a condition on our 8.2. So I'm just gonna also try and have this part here on our presentation of our diagram. Maybe it can help. All right. So the question was to draw a neat labeled circuit diagram of a 555 timer in an astable operation. Take note, it's an astable operation because it can be a condition that you are given a monostable operation. So in this case, they wanted you to be in an astable operation, which is the astable mode. So That is something like this that you're gonna need, guys. Your 5-5 timer in an a stable mode. From your presentation, you can have this as your circuit diagram, and also do not forget to present indication of being on of your transistors Q1 on there, and also you can also indicate the output signal of the voltages at the output. This part is also important for you to also indicate. Just like that, you'll be having, guys, your full marks. So there, I'm not going to talk much. Just make sure you go through your diagrams. And from there, they are saying calculate the oscillation frequency of a stable 5-5 timer, the one that we are just talking about. The one that you just drew, that is the one that you had previously. So they want you to calculate the oscillating frequency as you are given. The oscillating frequency, we also have our oscillating frequency. Remember, it can be calculated from this formula. But according to your formula sheet, also, I need you to see so that you do understand, because they were given values of A and B, this and that. According to your formula sheet, we have a condition where we can actually calculate our oscillating frequency here. All right. So our oscillating frequency can be calculated from this formula, 1,443 over Ra plus 2 Rb times C, which is the capacitance value, which is C1. So we can use that. We are given the values there of Ra, Rb, and also the value of the capacitor is there. So we saw that our oscillating frequency, if this is a stable 5-5 timer, or maybe a 5-5 timer, is going to be given from the formula 1,443 everything over what? So this is going to be Ra plus 2 Rb. So times the capacitance value, which you can write as C1. So depending with the textbook, they can use this as R1. This, they will use it as R2. Your R1 represents your Ra, your R2 represents your Rb. So depends with your textbook also. But according to your formula sheet, that's what you have. And also you're given A and B there. So that's 1,443 everything over what? Our Ra is given 90 kilo ohm. This is just 1,000 there. So it's just like 90,000. You can even write 90 times 10 to the exponent of 3. You can just write 90,000 plus 2 times Rb, that's 60,000 times 60,000 like this. Then whatever that you're going to have here, you must multiply this to the capacitance value, 1 microfarad. 1 times 10 to the exponent of -6. So that was going to give us the oscillation frequency, which is 6,871 in what? In hertz. Remember, our frequency measured in hertz. So be very careful with your presentations also. How are they given? Then you need to be very careful, like how these questions they are given in terms of your revisions, this and that. How are you given your questions? Then if you consider the last part that you are given, it was on your transducers. 9.1, draw a neat labeled circuit diagram for a closed loop system in which synchronous motors are used to control a radar antenna. A closed loop system. And after that, they want you to briefly describe what happens as soon as the transmitter rotor moves through an angle theta from the same diagram that you are given there. What is going to happen? All right, so if you're to consider on that part, I'm going to have this presentation that you can just go through as you are to have your revision, what they need you to have in terms of your diagram presentation. So make sure that everything is shown, the radar, antenna, the motor, everything, guys, you need to present. And considering that the transmitter TX and the receiver, which is RX, are in balance. as soon as the rotors are at the same angle. Remember, we need a condition now where we're going to have what? The theta being included. If the rotor of the transmitter turns at an angle of theta, the rotor of the receiver will produce an error signal to turn the motor. And thus the antenna also turns the rotor of the receiver at the same angle so that the error signal becomes a 0. So I just need you to go through your theory, also your diagrams. Explanations will be easier depending with the textbook that you are also using if you relate from there, because they might have explained something right the same way as that. Here we're just having like a common view of what they want you to have as your presentation, but answer also according to how you're having there from your textbooks also. Then on 1.2, 9.2, they needed you to draw a neat labeled circuit diagram of a precision switch in which a light-dependent resistor and an operational amplifier are used at the same time. You must have a light-dependent resistor, and we also need an operational amplifier to be presented. So this is what they needed you to have. And in this presentation, be very careful in terms of how you draw your components. As we are given on our diagram, you're going to have our LDR, light-dependent resistor, our transistors, and also the operational amplifier is given to the what? To the control circuit. So make sure you have resistors, but here, ignore the shading on resistors on marking guideline. Like what we have here is supposed to be ignored. The shading is not supposed to be there. So here they are just saying, please just ignore this. It's supposed to be a normal resistor that you are having. But if you do that, students to be penalized for shading resistors. So do not shade your resistors. Just draw your normal resistors the way that you're drawing, guys. Do not shade anything. All right. So that was your diagram. As you consider with your textbook, like I said before, you will understand much better to how these diagrams are, what is it that they need. But we're also going to have presentations of different sources so that you can see how these questions are to be given. So just make sure you go through each and every topic as we are having our introductions, that you work with your transducers also as a topic. It can help you to understand all the basics that are needed in your syllabus, and also to the oscillators. Each and every part are actually in your syllabus. So this is what we had, guys, from Meson African Motives. Till we meet again.